All right, so this video is just going to be a brief overview of the first law of thermodynamics. This is exploring that when energy is transferred, it can be transferred in the form of heat, but it can also be transferred in the process of work being done. Those two together make up your internal energy, recognized as delta U. And when we are dealing with chemical reactions, the work is going to be pretty limited. It would only happen in situations where the volume is changing while the pressure is remaining constant. And as long as you have a constant volume, which is what we tend to have in our bomb calorimeters, anything where, like a coffee cup, where the volume overall may vary, but the volume for that particular reaction will stay constant, the work term is going to be negligible. It's going to be zero because the change in volume would be zero. And so for reactions that take place under constant pressure, um, or reactions that take place with a constant volume, the energy term is going to be represented by enthalpy, which is going to be representing by your Q. And we're going to talk about how delta H differs from Q, because delta H is a state function while Q is not a state function. So when energy is transferred to the system, it's going through an endothermic change. You're going to have a positive sign for that value. The enthalpy will increase and your internal energy change will increase. When heat is being removed from the system, both of those will decrease because heat is being lost. If work is being done to a system, aka a syringe is being pushed on to make it become smaller, then you would have an increase in your delta U, but you wouldn't have any change in delta H because the heat being given off in the form of energy would not be any different. And the same thing if work is done by the system, the syringe is being expanded, that would result in a decrease in your internal energy, but would have no effect on delta H. So I said that state functions are going to be a little bit different than other quantities. State functions are only interested in your initial state and your final state. They don't really care about the path that it took to get from point A to point B. And so some examples of state functions are your delta U, your delta H, and your delta T. However, the beginning point and the end point will sometimes zigzag in the middle. And so things that would have a change in the amount would be more of your extensive properties, things like distance. Remember I said that delta H and energy, that delta H was a state function, while energy is not. Because depending on the type of change that's occurring, you may have to absorb energy or you may have to release energy before you can get from point A to point B. And so work would also fall in this category. So for these first two, we're just going to calculate delta U. You're being told what the signs are for Q and W. Here Q is negative, so that's an exothermic change. The work term is positive, so work is being done to the system. So when you combine those together, we get that the internal energy change is a positive one, that 41 kilojoules of energy is being provided to the system. Here we have an endothermic change where the system is doing work. You have a positive Q and a negative W. So when you add these together, you get that there are 65 kilojoules of energy that the system is losing as a result of this change in its internal energy. So it says, in which of these did the surroundings do work on the system? So those would be ones where the energy is increasing within the system. So that would have only been case A. So here we're going to look at just calculating the actual work term rather than being given the quantities. You're told the volume of an ideal gas went from 10 mils to 100 mils. It stayed at a pressure of 750 torr, and we want to calculate work. There is a relationship between joules and pressure volume units. 101.3 joules is the equivalent of 1 liter atmosphere. That is not a conversion I expect you to know. But again, that is a relationship that you can use to relate these quantities with very different units to one another. So if we want to calculate the work term, we need to have our pressure and we need to have our volume change. But if you look at that conversion with the work term to joules, we need to get our pressure in atmospheres. So we're going to use our relationship that 760 torrs is the equivalent of 1 atmosphere, and that will get us the P part that we need. Now we need to get our volume in terms of liters. So we're going to take the difference between our two volumes. 100, we started at 10, we went to 100, so the difference would be 90, but we need to convert that to liters by dividing it by 1,000. So that cancels out your torrs and your milliliters. And now you have your pressure, which is almost 1 atmosphere, times the volume change in liters, 0.09. And we see that that gives us a negative value for our work term, because for that syringe to expand, the system had to do work to allow that expansion to occur. So this is atmospheres liters, but because energy is represented typically in units of joules, we're going to convert it using that relationship I talked about previously. And when we do that, we see that 9 joules of energy was given off by the system to be able to expand the syringe. You could also use this to find Q if you had the mass of the gas, the specific heat of your gas, the temperature change your gas went through, and then you can combine those two together, the Q and the W, to be able to calculate your change in internal energy.